Hello everyone, my name is Mugara Albert uh, from Group 37, and our project is titled Graph-Based Reasoning, Large Vision Models for Ugandan Sign Language, Translation in Infectious Disease Screening. What is the goal of this? It is to create an AI system that helps doctors and nurses communicate with deaf patients during medical checkups, especially like in rural areas where there are no interpreters. Start with the background and introduction. Uganda has over 500,000 deaf people, and there are more than 40 million across the sub-Saharan Africa. In rural clinics, there are no sign language interpreters, meaning deaf patients cannot easily describe symptoms. So this leads to delayed diagnosis and higher deaths from diseases like malaria, TB, cholera, and so many others. Our solution, we designed an AI system that translates Uganda Sign Language in real time using cameras. It automatically fills in medical details like fever, cough, and symptom duration. Using graph-based reasoning, the system achieves high accuracy. The impact is faster, up to 60% quicker. Early detections of outbreaks and better health access, supporting the Sustainable Development Goal, that is the good health and well-being. When we go to the related works here, we reviewed existing research papers in AI and vision models, and where we saw the graph attention networks, but with accurate but limited to static mode data. Then also there is vision transformers, the VIT. It has good for image clarification but need massive data sets. But then there is spatial temporary, that is the GCNS, where it works on skeleton data but are not optimized for sign language. Then also voice-based sign recognition, that recognizes isolated signs but lacks continuous translation. So, and one of the gaps we identified in this, but none of these models focus on Uganda Sign Language or real clinical settings. There is no medical data set, no deployable model, and no red flag system for healthy safety. But our work fills all these gaps. So now, to start with the problem statement, deaf patients can't describe symptoms. Interpreters aren't always available. So this delays diagnosis outbreaks. So now, the computational problem is that we must recognize continuous sign language at least 0.5 to 33 seconds. Handle different signing styles and video quality. Extract 8 key medical slots, all in less than 300 milliseconds on an Android tablet. So now, one of the research questions and objectives of our system here is can a graph attention network, that is the GAT, capture Uganda Sign Language effectively? How can we combine RGB video plus pose data for better recognition? How can we transfer learning from existing sign language datasets like the ASL or Ghana Sign SL, that is sign language, to Uganda SL, Uganda Sign Language? How do we ensure clinical safety and red flag alerts? So, and the objectives is that to design a GAT that recognizes 468 body landmarks with 10 to 15% error rate. So, and achieve at least 85 to 90% slot accuracy, maintaining valid medical logic, and run in under 300 milliseconds on tablets. So, and the research contributions, we have the graph reason recognition, a 4-layer GAT using both skeletal and semantic edges that is 20 to 30% better than the one of CNNS. Then also we have this, the FST constraints, that enforces valid medical question answer logic, improves accuracy by at least 15 to 25%. Then we have the production system, the first Ugandan Sign Language medical AI in East Africa, under 200 MBs, working offline, supporting red flag detection, at least 95% precision. So now the system architecture here. This system starts from the video input and passes through these stages. The first stage is the pose extraction, that detects body, hands and face landmarks. Then also that connects jointly and logically, that's the graph building. Then from there it goes to the GAT model that reasons over the structure, classify medical signs. Then the last one there, it is the inference output that displays recognized symptoms and duration. It's an end-to-end AI pipeline optimized for real-time use. So now on the model 1, that's the pose extraction architecture, we use the blaze pose, the manual hands and the flame face models. These detect 4, 6, 8 landmarks for the body, hands and face. That's where our focus is. So the optimization, we have the skipping face detection that gives at least 3 times speed increase. The batch processing of 4 videos at once. Final data is downsampled to 75 nodes for the graph network. So we go to the model 2, that was the graph attention network architecture, where this is the core of our model now. It inputs 75 nodes, each node that is the X, Y, Z position, and then the layers, the 4 GAT layers, 64 to 128, then from 128 to 256, then to 8, and it uses 8 attention heads for parallel reasoning. So the mathematical idea here, we use the linear transformation of each node's feature, and then to compute attention scores to learn which joints influence others. Then also we use the aggregation neighbor information. Then also lastly it was the output probabilities for 8 medical symptoms like the fever, cough, hemoptysis and so many others. So this structure helps the model understand relationships between the hand, the face and the body, as you can see here. So because the HI here, it was the feature of the node, the W stands for the weight matrix, A the attention, as it is very clear here. So now when we proceed to our dataset now, our dataset is designed, it has a total of 9,877 sign language videos with 500 analyzed for testing. All videos are of high quality, 1080 pixels, 30 fps and uncorrupted. So now these, but among all these, only 27 are medical related, such as the doctor-patient interactions, mental health, infectious disease, emergencies and treatments. So the duration of all these, mostly 5-second videos long, perfect for real-world signing. So our dataset, this one is reliable and suitable for training and testing, because we did it and we tested it very well. So now I'm going to take you to the EDA and the visualizations. So this section shows how explanatory, data analysis, visual checks of pause points, sign durations and dataset distribution. It helps us confirm balanced data and clean structure, ensuring our model learns effectively. Right from here, the first one here, it is showing you the frequency on the x-axis, then on the y-axis it is showing you the duration. Same applies to here. Y-axis here there is frequency, then here there is the frame count. So What were the results of us training this and the validation? During our training, we monitored accuracy and loss curves. So now the model converged steadily, proving good learning. Validation accuracy reached around 57 to 60% when we trained it, which is strong for early testing and maybe using the proxy data. Now the results and inference speed, the total processing time was 150. But under the 150 we have the post extraction, which is 28, graph building, which was 12, and the GAT training, which was 85. So this meets the less than 360 milliseconds requirement, meaning real-time translation. So now on this part here we added explainability to see which joints the AI focuses on. For example, like the sign fever, it pays attention to the right pink, the left hand finger, then the left index finger plus the chest center. So the model actually aligned the hand to chest motion, confirming that it reasons correctly like humans. So now our model selection and deployment, we selected the media pipe plus the GAT for deployment, but the OONX allows export to Android apps, and that's why we used it. And the pipeline here is the MP4, then from the MP4 to the media pipe, then through that process, and it runs offline. A lightweight, that is the 110 MBs, and they are under 250 meters per second, perfect for rural clinics with limited connectivity. So now here on our demonstration, here are some images where the avatar is communicating here via our Android tablets. For example, the patient says, I have fever for 4 days. The app outputs yes, duration 3 days, red flag, can say serious symptom. So it then saves data in our JSON format, compatible with the hospital records. So now the limitations and mitigations that we faced along this, we have 3.18 pose extraction errors, that and how do we plan to fix it is to add a retry plus image augmentation. Then 57.5, that was the accuracy, and how do we plan to fix that? Like by collecting 500 plus Uganda Sign Language videos. So we also faced the no real Uganda Sign Language data. So but we want to partner with the Uganda Deaf Association, ensure that we get this data. Then also there was missing FST rules that we plan to get by adding post-processing for logical flow. So we successfully built the first real-time Uganda Sign Language translator for the medical use. It runs very well with 250 meters per second with the 43.3% accuracy, which supports the FHR and the red flags alerts, showing great promise for inclusive healthcare AI. So now the future works. We plan to collect over 1,000 real Uganda Sign Language videos, fine-tune the GAT model, add medicological rules, conduct a clinical trial like one of the hospitals here we have Mulago, and then expand to other local languages like the Nyankole, Uganda, very many, because in Uganda we have very many. References, we use these ones, like I had already talked about them, the GAT, the Blaze Pose, PyTorch, and the Sign Talk Ghana. So we thank you, our supervisor Dr. Marvin, and the rest. Thank you for listening.